All right, good afternoon and welcome to the Scripps Technical Forum. I want to extend a welcome to you this afternoon, and I appreciate the ability to shift gears because we did have this originally scheduled a couple weeks ago and we had to change the date, and I appreciate your help on that. But anyway, I'm Douglas Alden and I'm the lead engineer for the Center for Western Weather and Water Extremes here at Scripps. In addition, I function as the STF chair and get assistance setting up and running STF from my colleagues here on campus, Gwyn Nero and Vanessa Scott. Gwyn is the Director of Corporate Affiliates, Business Development, Industry Outreach and Innovation, and Vanessa is an Industry Relations and Innovation Analyst. If you have missed any of our previous presentations, you can find them on the Scripps Technical Forum playlist on the Scripps Oceanography YouTube channel. You can also find links to PDFs and recorded webinars through the STF website. Please know that today's presentation is being recorded. And that in mind, if I can get my thing to go, here we go. So if you came in, if you need to ask a question, you can either raise your hand or you can probably just interrupt and unmute yourself. If you're on the phone, just hit *9 so you can do Q&A, and please use the Q&A function to type in your questions. I'll be monitoring it and can ask Doug to answer those as they go on. So today we have Doug Moran. He's the co-founder and Chief Technology Officer of Okika Technologies. Prior to starting at Okika, Doug was Vice President, Worldwide R&D for Ramtron International Corporation, now part of Infineon Technologies. He participated in several startup ventures in the high-performance analog and mixed signal semiconductor space and held engineering and management positions in a number of semiconductor companies, including Conexant, Fairchild Semiconductor, Microchip Corporation, and Brooktree Corporation. He started his career in semiconductor engineering and design at UCLA, extended his business acumen through executive development training at Stanford University Graduate School of Business. So please welcome Doug Moran.
Well, good afternoon, everybody, and thank you, Douglas, for that introduction. I'm really happy to be here. I can't see who all is on the line right now. About how many folks do we have here?
We've got eight attendees.
Okay, great. Yeah, so thank you, Douglas. So this is just briefly a company profile. I think Douglas already covered most of this, so I won't spend a lot of time on it, but if you need more information, certainly can contact me or check out our website at okikatechnologies.com. So this presentation is a brief overview of our dynamically reconfigurable analog matrix, which is an integrated array of analog functions that can be dynamically reconfigured during system operation. So different configurations of DynAMx chips perform a wide variety of analog functions. And the real power of this system is the ability to change the configuration, analog parameters, or even the complete functionality of the chip. So for example, transitioning one application, a customer of ours is using it for sonar, and they reconfigure the chip to go from transmit mode to receive mode while they're waiting for the sonar echo to return. Configuration is very fast and switches over in just a matter of a few microseconds. So the programmable analog solution is equivalent to an FPGA in many ways in terms of predefined silicon architecture, programmable fabric, software function library, and an EDA tool flow that supports all of those features for the FPGA. And so for those of you who remember kind of the history of FPGA, it didn't really take off until the tool flow was in place, which really simplified the burden of having to program the internal fabric of that design. So the FPAA is very similar in terms of it's got a silicon architecture and programming fabric, configurable I/O and analog blocks, And configuration is done via CMOS switches on chip. So that includes signal steering or routing, function switches, equivalent resistors. This is a switch cap design, so resistors are implemented as switch capacitor circuits. And switch state is saved in a double buffered memory, which is equivalent to SRAM. And what that double buffer allows you to do is run the chip at one configuration and load up a new one while it's running. And then in one clock cycle, it will switch to the new configuration without interrupting operation. So just some fundamentals here, and I do have a demo at the end. So if anybody wants me to skip some of this material and just jump to the demo, please let me know. I'm happy to do that. So in terms of configurable I/O, there's analog, digital, and continuous analog functions. A configurable analog block, which holds all the basic analog functions of comparators and op-amps, AD converters, etc. The programmable fabric is a matrix of switches to route signals around the chip. And the whole system is designed for simple download and configuration of any elements within the design, or all elements or groups of elements. And the software tools handle all of that for you, so the engineer doesn't have to worry about which switches go in which direction. The configurable analog modules combine configurable analog block functions to create more complex systems. I'll go over that in a bit, more detail here in a little bit. And then in terms of tools and software, we do have internal tools to support unique CAM development. If there's a CAM requirement that isn't already in our library, we can go off and develop it for you. The tools support straightforward high-level analog design using either schematic capture or scripting language. And there's a simulator built in, which is a time domain simulation. And it's pretty much what you see is what you get. It's very accurate. Having been part of this design for well over 10 years now, it's been highly optimized. And the configuration can be downloaded very quickly, either as a configuration bitmap, or the tool will output a series of C code files that creates an API you can load on your system MCU, and that gives you dynamic control over all the functions on the chip as well. The block diagram of the chip. You can see in the middle, the heart of the design are the 4 configurable analog blocks. There's plenty of analog I/O. The 4 on the left are have built-in op-amps as well. So there are a total of 12 op-amps that are usable on this design. And then a handful of control signals and so forth. These are all defined in or described in our data sheet for. To continue, the configurable analog block, what's internal to that block, and this is what makes up the fundamental element of the array. There are 2 op-amps, a comparator, a SAR A to D converter, and of course the switches that can act as either switch capacitors or as capacitors for feedback or feed-forward circuits. And of course, there are local inputs that come from other cabs and global inputs that come from off-chip or go to off-chip. Just to kind of highlight the configurability of the I/O, there are built-in amplifiers in each I/O, and they can be configured as inputs or outputs. You can bypass the amplifier, use them for standalone op-amps if so desired with external circuitry. And so move on a little bit here. I'm going to skip a couple of slides here because we lost some time. And the basic goal of this design of this system is to enable engineers to really focus on analog system design and leave the challenges of analog design to the tools and the chip itself. So designers don't have to worry about issues like offsets or on-chip reference levels. Those are all generated on-chip. Routing parasitics are accounted for both in the chip routing itself and also in the simulator. Stability and compensation is managed internally as well. And environmental effects like temperature, supply voltage, and process variation. The typical analog design functions within about 3% of what the simulator says it will do, which is way better than most analog circuits can achieve. So the design flow starts out with the capture, which is a simple schematic that has various analog functions in it. One could also use a scripting language rather than a schematic and end up with the same system. And then once captured, as you place components, a dialog box opens up. So in this case, this is a filter, a bandpass filter. It's being set to automatic filter topology. So the system analyzes the best topology for the filter type. And you can set the corner frequency, the gain, and Q factor. And you can see the ranges that each of these can have. I'll talk a little bit about that more later. And then the simulator that's built in, as I said, it's what you see is what you get accurate. So this is just showing the signal nodes that are on this schematic, color coded obviously, so you can tell which signal you're looking at. And then we have a evaluation board that can be used that plugs into a PC via USB port, and you can download the configuration for your circuit into the chip, and then evaluate it on your benchtop. And if there's something you need to adjust, you can just go change parameters or modify the schematic and then go through this loop again. It's an iterative process, but it moves very, very quickly. So in terms of capture, we have a library of analog functions. And this example is an ultrasonic transceiver, a very simple one that I wanted to use just to kind of demonstrate capabilities here. Parameters are set in the dialog box, as I've already discussed. The simulator features, it allows engineers to simulate the circuit with inputs and verify outputs are within spec. So it has built into the tool signal sources. There's not a lot of analysis other than waveforms, but those waveforms can be captured and stored into data files on your computer, and you can post-process those if you wanted to do something like an FFT or other analysis on it. And then the evaluation board, of course, looking at the configuration of that board, and then you can compare it directly to what's in the simulation and what you expected. We also have a DynAMx Filter Lab, which is a filter design tool that's built into the software. This tool is actually pretty powerful. Allows you to select the type of filter, the approximation you want to use. You can actually go and move the template around graphically to get the waveforms you're looking for, or you can go enter directly the parameters for the filter type. And once you have the parameters all set up the way you want it, you just click on to Anodyne Designer 2, and this will automatically load the filter schematic into DynAMx Design Lab schematic. And here's an example of the library of CAM functions. You can see there's quite a few of them here, so I'll just kind of briefly describe a few. There are 4 8-bit ADCs. Each ADC uses 2 op-amps. So if you're doing an ADC, for example, you're using 2 op-amps for that, which leaves you 6 for other functions. Comparators, summing circuits, there's a delay element, which I'll give you a little demonstration of here in a few minutes. The 4 basic filter types, various gains and gain switches, so you can adjust gains and use these as analog multiplexers as well. math functions. There's a fairly wide variety of math functions, signal sources. So these are fixed signal sources. You can change the frequencies and the amplitudes via the API or in the schematic capture. And there's also an arbitrary waveform generator. You can load form into on-chip memory and just run that waveform directly. Peak detectors, various other filter types with input multiplexers, some integrators. Any questions so far? Okay, here's an example of a biquadratic filter dialog box that comes up to fill in the parameters. Being a switch capacitor filter, there's a group of clocks on chip that you can select from to set the filter switch frequencies, and then select the filter type, topology. This is a two-phase non-overlapping clock architecture to help minimize noise, so you can select which phase you want to use for this particular filter. You can select the polarity, and then of course in the bottom parameters, corner frequency, it gives you the ranges for those frequencies, gain and quality factor. And these numbers are adjusted based on what clock frequency you're running. So if you wanted to run higher frequency signals through this, then you could select the higher frequency clock. Also notice that there's a documentation here which is somewhat of a data sheet for each CAM, and then the C code API is listed along with that. And here's a comparator, same thing. You have various parameters you can set and options. And then just a simple inverting amplifier, and you can see the gains. The only parameter here goes from 0.01 to 100 linear gain. The designer or the design tool also supports multiple chips in a system. We have one customer who actually has 32 FPAAs in their system, and the simulator supports that as well. So you simply drop a new chip into the schematic and connect it up the way you want. The software supports configuring all 32 or however many you happen to have FPAAs through a single SPI interface port, so you can conserve those valuable MCU GPIOs. So configuration and reconfiguration, and this is the real strength of this system, is how to configure this either statically, in which case you can just program it once, or you can configure the chip, hardwire it so that it will read its configuration out of an E² memory that's on the board. You can do dynamic configuration, which is, it's essential to most of the systems that we're in today, as it does support signal conditioning and calibration, fine-tuning challenges of sensors, including aging, and in control applications supports adaptive analog signal processing as well. So it allows, I think I've said this several times, for on-the-fly dynamic programming while the device is running without interrupting the outputs. So I'm going to skip that, kind of already talked about it, and I'd like to jump. If there aren't any questions, I'll just jump to a couple of demonstrations.
I have a question, maybe.
Okay.
So maybe you said it, but how fast how fast can the signals be that go through this system? What's the bandwidth of the?
So the Unity, for the current product that we have released to production, Unity gain bandwidth is about 40 megahertz. So of course you trade off bandwidth with gain when you set the parameters on the device.
Yep.
We just received, or currently testing, new silicon. It's basically the same chip, but we moved it to a faster process. And that has 130 megahertz unity gain download, roughly 3x the current chip.
Okay.
And that'll be available in Q1 of next year.
Do you sell these like a demo board? Is that something that we have, like you just buy a demo board?
Well, yeah, we can sell the demo board, which I think I had a picture of here. Pull it back up. So this is the demo board. And then it has one chip on it. We also have versions of this demo board with 2 or 4 chips. And of course, we sell the chip itself into the open market for semiconductor products.
Okay,
And
thank
actually,
you.
our largest customer right now is. Can you hear me?
Yes.
Okay. Our largest customer right now is the largest manufacturer of sonar equipment in the world today, and they use our chips right in the heart of their system. So I wanted to kind of walk through this quick demo. Actually, I have 2, if you don't mind. Each one will take about 10 minutes or so. Can you see the screen now? It has the outline, the silhouette of the chip on it.
Yes, we can see that.
Is there something anybody would like me to try to enter here, so you can actually see it in action? You know, some kind of a filter or gain stage or analog signal processing function.
I was kind of interested, was there an ADC on there?
There is an 8-bit SAR. Yes, it's very low frequency.
Okay. That might be interesting.
The A to D converter.
Yeah.
Okay.
Thanks.
So what I'm going to do is go up here to this little symbol, which brings up a library of components. I'm going to select the ADC SAR, and I'm going to just drop it right in the middle. And this is giving me a message that clock B has to be 16 times the frequency of clock A. So I'm going to set clock A to I'm going to have to change the clocking on this. So I'm going to go up to setting. And this gives me a dialog or a control panel to control the clock frequencies. And what I'm going to do is lower the system clock frequency down just to be able to quickly show you this. And I've got 2. Sorry, I'm having problems with these clocks. I didn't expect this question.
It makes the demo more real because these are the things that we encounter. So appreciate you taking the time to take on these tasks.
Oops. There we go. Okay, so we'll set this up to, well, it's not giving me the choice here, unfortunately. So I'm gonna have to dig into this and find out why, but we'll just go ahead and see what it does anyway. I'm gonna create an input and make it a bypass. Or if you prefer, I can go up here and pull out a oscillator, pull out a sine wave oscillator and use that as the input to the A to D converter. And I'm going to make it a 1 kilohertz signal. Oops. Better frequency here. I'm feeling really stupid right now. Sorry. You know, I'm going to just go start over. I think I'm going to be setting it messed up. There we go. Okay, now I'll bring my sine wave in. And I'm going to make that I apologize, folks. I almost never use this AD converter, so just bear with me.
Yeah, and sorry, I was the guy who originally asked where I didn't really. I am very interested in the analog functionality of it too. I thought it would be something that's just a quick little tack on there.
Okay, can I get back to you on this? Because I do have a demo that I think you might be interested in if you're interested in sonar.
Okay, yeah, that'd be great. Thank you.
Okay, how do I do this? Sure. Okay, this is a design I put together a few months back. This is a ultrasound transceiver, and this is my first cut at it. Today I actually have hardware. This is just a single channel, but I have hardware that demonstrates 6-channel ultrasonic transceiver. And the way this is set up is there's 2 chips here in use. The chip on the left is the transceiver itself. The chip on the right I'm using as a test circuit. So the transceiver is using an on-chip sine wave generator that goes through a switch filter. And what that switch does is selects between two different inputs, one of which is an off-chip sinusoid that's set to 0 amplitude. So it's basically a DC signal. And then the other comes from the sine wave on chip that's being generated. And then there's a signal source driving into one of the inputs that, and this is set up to be a just a pulse with a duty cycle of 5%. And so that triggers the ultrasonic output. And outputs go off chip and come back onto the second chip and then go through a delay element. And that delay is set up at 1,000 microseconds. You can see it has a pretty long range here that you can use. And then there's a gain stage. And the gain for this, and this is to simulate the effects of the ultrasound going through water column. So this gain stage is set to 0.01 linear. And then bandpass filter to simulate the transducer for ultrasound, and also more attenuation of the signal. So this is set to 0.01 as well. And then the output of that signal is routed back into the input of the transceiver. And this is the input pad settings. I've got that set to be a low offset chopper to minimize the effects of offset voltages. And I've put in 60 dB of gain into that op amp. And then there's two stages of biquadratic second order filters. And these are set to the corner frequency of 40 kilohertz, as you can see. And this first one has a gain setting of 10. And then the second one, just the unity gain. So between the 60 dB gain of the input buffer and unity gain of the 10x gain of this filter, we get pretty reasonable results for this particular simulation. Now to actually simulate it, you'll notice these probe pads, these scope probes that I have set up on the chip, various internal nodes as well. So I've got the simulator all set up to run 1.5 milliseconds. And there's some other switches here you can set up as well. I'll just go ahead and run a simulation on this. And you'll see the blue signal is the pulse that would come from the controlling circuit, whether it's an MCU or some other switches. I'm sorry, can you see the waveform?
Yes.
Okay. That pulse switches between the sine wave and the DC level. And the reason I'm using a DC level with a zero, or a sine wave with a zero amplitude is to get the reference voltage correct. So here's the transmit signal, and then the signal is coming back into the receiver. You can see the scale here is about a 300 microvolt signal coming back into the receiver. And then this is the output in green of the spinal comparator, the slicer. So I think I mentioned I have some hardware I could show you that uses this basic design. But in that hardware, it multiplexes between these 4 primary inputs and 2 of the secondary inputs to create a 6-channel ultrasonic transceiver that allows you to go through each channel one at a time, or a selected group of channels, depending on what you're looking for. And that one, I've got extra filters and slightly different gains, and they're all adaptable. So the way I implemented the other system was using the API and set it up on the Raspberry Pi platform used the Raspberry Pi to develop a graphical user interface to demonstrate all 6 channels running and showing the echoes come back, and the range calculation is all built into that. So the GUI actually cycles through all six channels and creates 6 different transceiver designs, and then adjusts the gain over time. So gain is increased as signal attenuation is increasing as well. Any questions about that?
Yeah, what is the input noise on that amplifier? Did you already go over that?
I did not. There's quite a bit of data I can provide to you. Now, when you say input noise, are you referring to
Input refer, say, voltage noise and current noise. So if this was used for a sonar element, the noise figure of that particular amp is very important, you know, but even before filtering and all the other really good processing that you've shown us, we want to make sure that we have a chance of reaching whatever noise figure we need for our application. So it would be important that of all the analog parts, that's one of the most important part of one of our acoustic arrays is that amplifier. The rest are great. We need all those things, but that figure of merit is probably the most important.
you're talking about this input amplifier?
Yeah.
I don't think it's in the documentation, but let's see if it is here. No, it is in the data sheet, so I'll get that information for you. And I'll send it off to Douglas. So you're looking.
Oh yeah, that would be great. That would be great. Right now
I'm sorry, go ahead.
Our group right now, we're working on an acoustic front end, and so it'd be very interesting. We're racing ahead with application-specific ICs, and this technique looks really, really promising. It's just that, you know, the data is very important for us. So yeah, that's kind of timely. If you could get us the front end specs, you know, as soon as possible, then we can make some very crucial decisions. So thanks for that.
Sure, I'll get that to you this afternoon. Just out of curiosity, what is a good number for you? What are you looking for?
Oh, well, say, you know, a typical resonance for piezo is in the order 100 ohms, right? So we want to be able to get the down to about a you know, something like a nanovolt root hertz noise density, because then that matches the noise of our transducers, something similar to that.
Okay, and now did you say a nanovolt per hertz?
Yeah.
Okay. Got it.
On that order, you know, so the exact number is not important because there's other things like the current noise and what we're trying to match to. So, but that is a good acoustic front end amplifier is on order 1 nanovolt per root hertz.
Okay, I will get that for you. What about SFDR? Is that important to you as well?
Yeah, that's an important thing. But because you have so many other like variable gain, all these other fancy features, once we can capture the first few, once we can boost the signal into the range of the programmable gain part, then those figures are less important because we can manipulate the gain. The spurs in the input amplifier are important, but after that, we can manipulate the signal using your gain stages and filters. So those are important, but we're much more flexible on FDR, the spurious-free dynamic range, than the noise at the front end.
Okay, great. That's good to know. Thank you.
Yeah, Doug, if the input amplifier that's on chip doesn't have the specs that Mike's looking for, is there opportunities just to use a discrete amplifier outside the chip and pump that into the system?
Yes, definitely. We do have customers that do that as well, but not for sonar applications. Would you like any information on, I guess, what external components would normally be used for that, or is that something that I'd be happy to look into that for you?
Yeah, that would be helpful to know what you can hang off the front end.
Okay. All right. Anything else?
I was thinking that looking at some of the questions that were submitted before the presentation, one of them was regarding power and speed limits. I mean, I think you covered the speed limits based upon Mike had a question earlier, or Matt had a question earlier that asked that, but can you address what are the power requirements for the system?
Sure, that's it's highly dependent, of course, on what functionality you enable on the chip. The easiest way to determine that is after you have your design in, you can pull out this little tab over here, and it actually gives you a power consumption estimate, in this case is not showing. So I'm gonna try it on this one, I guess. So for this design with a delay element, a gain stage, a biquad bandpass filter, about 88 milliwatts. And this is dependent also on duty cycle. So the chip does have a power down mode and a brownout mode, so you can reduce that power slightly and then power it up when you're ready to use it again. But that's one of the downsides with switch capacitor circuits is they tend not to be very good for low power applications.
What's the warm-up time when you bring it out of low power mode?
I would have to get that data for you. I'll send it out this afternoon as well. I think it's relatively fast because the configuration is saved if you don't power the chip all the way down. So it's just a matter of powering up the amplifiers and the reference voltages and the time it takes for them to settle, which I think is pretty fast.
Any other questions from the community about this design or any of the specifications regarding the chip that we haven't already covered?
I missed the first part of the sequence. So did you guys go over the evaluation kits that are available and pricing, singles, and volume, and that kind of thing?
We didn't talk about the pricing and volumes. That's certainly something we can discuss. On the evaluation kit side, we do have a number of evaluation kits that range from 1 FPAA per board to 4 per board. We also have in development a Raspberry Pi platform. It's a Raspberry Pi add-on board that plugs right onto the Pi. It has 4 FPAAs on board. Pricing for the single FPAA evaluation board is $199, and that can be ordered directly off the website. The chip pricing, it ranges from just to $10, just depending on volumes. That's for the current device. The next generation device, which I mentioned will be out in Q1, will be significantly lower cost than that.
Okay, great. Well,
We
thanks.
haven't put pricing on it yet.
Did you have any more demos, Doug, or was that it?
No, that's all I had, unless there's something specific somebody wants to see.
You have a lock-in amplifier demo?
I'm sorry, what?
A lock-in amplifier, synchronous demodulator, or any kind of demodulator.
Like a PLL or something like that?
Well, I was thinking specifically of something like, since we're doing quadrature demodulation on the sonar, and we're doing synchronous demodulation for our sensors, it would be nice to have some, I can see the building blocks there, but do you have, let's say a multiplier? Is there a switch capacitor multiplier block that you can, I don't really need to see a demo, but is that something that's readily available?
Sure. Yeah, that's right here in the library. There's a multiplier or a multiplier filter.
And then of course you have the ability to just use analog switches to make discrete multipliers. And so it seems like we could make ourselves, what I'm excited about is that when we're designing a circuit on the bench, even if we have to go into the low power or ultra high speed range, we could have these things as laboratory units to test, even if they don't fit in our field, because half of us are in ultra low power and the other half are in ultra high speed, and then actually there's a lot of crossover in the middle where these chips would be ideal. And I would like to have one right now, to have on the lab bench to experiment with the circuits that we would then develop in our, maybe micro power circuits that are based on a template we designed with these creative chips. So I'm really looking forward to testing these things out.
Yeah, that's great. And that's, many of our customers start out along those lines, either for educational purposes or for very quick prototyping, turn and burn on a new design iteration or alternative design very quickly. And then they can go to more of a standard implementation if the FPAA isn't low enough power, it doesn't provide exactly what they need. We also offer design services so that we can customize these chips if needed. If you need a wider bandwidth amplifier or low noise amplifier, we can certainly do that as well.
Well, thank you.
Mm-hmm.
All right. Well, if there are no further questions, or we can wrap it up for this technical forum.
Great. Well, thank you all very much for inviting me and for listening in. Feel free to contact me directly at doug.moran@okikatechnologies.com. And certainly check out our website. You can buy the evaluation kits there as well as sample parts if you want.
Great. And then yeah, we'll provide you with a list of the participants, and we can reach out, or you can send some of those answers to the questions that we had, and we'll send it to everybody that's on the list. I really appreciate your time today, Doug, and really excited about this technology.
Great. Thanks very much.